Hello, everyone. So, welcome back to today's episode of proving stuff within the Rocq Proof Assistant. In the last video, we defined a whole bunch of things, including nodes and edges and graphs based on these nodes and edges. And we did some very basic proofs. Uh, and we also defined this notion of a path. That is a connection between nodes through multiple edges. And we define this path length to determine the length of the path. So on today's video, I would like to first add some properties about paths, and then we also might want to change some parts of the definition about graph, but more on that later. So for paths, to start us off, we had like a bit of a discussion that we changed this from a prop to a type. And I think we're going to go ahead and change it back into a prop as it was before. So the main reason for this is if you have a piece of code, like if you're trying to run a program, you have a version of it that looks like data and a version of it that looks like a mathematical property. So in here, as we see inside of this path length function, this p, which is like the object, looks like this mess of stuff that contains a node, an edge, and a proof, and a subsequent path. So we are inductively constructing this path when it's a type, and we carry around this piece of proof code within the definition of the path every time we have this. So this is not exactly ideal for when you're writing code. You don't want to contain this piece of proof every time. You instead want to have something simple that doesn't have it, and basically just pull out all of these proofs outside of the code and enforce it afterwards. So if we were to look at how paths look like within code, like how we want to represent them when we're writing code, the most intuitive way is to say definition C code, or what should we call it? Comp path is going to be a list of nodes. And then path is going to be this inductive version over prop. So right now, with this definition comp path, it's just any arbitrary list of nodes. We don't actually know that it belongs to a particular graph, or that it is a valid path within this graph. It's just an arbitrary list. There's no assumption made of it. There's no proofs. Whereas path is the proof that it is a valid path. And there's like a somewhat of a correspondence between these, where every path can be expressed as a comp path, and every comp path with a proof that it belongs within a graph can be reconstructed into a path. And the way to represent that is to do an extrinsic formulation of what a path is. So here it's basically an intrinsic formulation. We are constructing this path from this, we are carrying the proof around in every single step in here. this is the proof that we're carrying around. We're building up based on this proof. So all representations of paths are exactly corresponding to paths. But this one needs to be extrinsically verified. So it's like we can build more things that are not paths, and then we need to like impose restrictions on these to make sure that we are only operating over valid paths. But we'll go back to that later. So right now we want to work with just this intrinsic formulation, and instead of we won't be able to define the path length, but we will be able to define the length of this comp path, which is just the length of the list. But we do want to be able to do some nice properties with this path. So I guess we don't need this part anymore, the length. And this is the final theorem that we do want to prove. I'll go ahead and these things might still work. This one will not work. And this one will not work. But the rest should work. Yep. So we can no longer compute the length of this path because it's just a prop. It's not like a piece of data that we're carrying around. It's just a property about two nodes. But we can do this final proof that we want to do, whether there exists a path or there doesn't exist a path within the graph. But the thing that I wanted to prove first is that path is a partial equivalence relation. So what a partial equivalence relation is, we have three things that define an equivalence. It is reflexivity, symmetry, and transitivity. So if you haven't seen this before, I can write out the things for natural numbers and equality. So so nat is reflexive is for all n that is type nat, n is equal to n. This means reflexivity just basically means that the equality compares any two things within the type equal to itself. And whenever something is reflexive, so intros n, we want to prove this reflexivity over the equality, we can use this tactic called reflexivity. And it solves it automatically. This reflexivity needs to be implemented in some way by the user if you want to define these for your own pieces of your own propositions that are reflexive. And reflexivity is just like a tactic that finds all the things that are reflexive and sees which ones apply in this particular situation and applies it to solve the goal. So we can train it, say, oh, this is something that is reflexive, so you can add it to the list of things that are reflexive, and you can use that to solve the goal. But I'll first go over the other versions. So we also have symmetry, that if we have two natural numbers and we have that m is equal to n, then we have that n is equal to m. So this basically tells us that we can flip the proposition, and we will still have the same. We will still know that it's true even if it's flipped. So instead of reflexivity, I guess we also need to introduce H here, our hypothesis. So we have m is equal to n. We want to prove that n is equal to m. And we have this tactic called symmetry. So very similar to reflexivity, symmetry works on things that were defined by the user to be symmetric. So it sees that this is an equality, and we know how to prove symmetry for these equalities. And so symmetry will just flip the equality. And now we have the hypothesis H, so exact H. Because we just know that this proof is done by this hypothesis that we have, H. And then the final thing for natural numbers is transitivity. So if we have that n is equal to m, and we have that m is equal to p, then we should have that n is equal to p. We can basically start with n and go through to p by traveling through m, and this equality still holds. So here we have both of the assumptions, h1 and h2, and we would think that it is just transitivity, if I can spell it. But this tactic will be angry at us a little bit. It says that it's missing an argument. It doesn't know, just from this n is equal to p that it looks at, it doesn't know how to get between n and p. We know that there is something that it needs to travel through to finish the equality, but the tactic itself doesn't know what it is. So we need to specify to the tactic that we want to be traveling through m. And now it splits it up into these two goals, the n is equal to m and the m is equal to p, which are both within our context. So we can just finish this with auto. Cool. So now the interesting thing about this m here is we have this other tactic that doesn't need to specify the m, called e-transitivity. So to compare, let's first run it. So before, it didn't know what it was that it needed to put in for the m, so it couldn't actually run the tactic. But with this thing, it puts an evar. It's basically a variable that we don't actually know what it is. And as we do the proof, it will become determined what this thing needs to be to finish the proof. And once it becomes determined in one side, it becomes determined in all of the other sides as well by a unification property within Rocq. So this first thing over here, we would be able to determine, find the things in the goal that look like n is equal to something, and it does find this n is equal to m. And then we can unify this question mark y to correspond to this m. Rocq is able to find this goal and substitute it in for m. And then this, when we're substituting it into here, it would realize, oh, this is the same unification variable, so this must also be m. And it finds that m is equal to p on this side. And so it would be able to directly prove this, saying that the m is equal to n. So I guess we'll do it in two steps. So in the first step here, n is equal to question mark y, uh, we can do exact h1 to be able to determine exactly that, like, it should be this h1. So even though this is a question mark, it should be filled in. Let's see if this works. Yep. So that solved the first. That solved the first thing. And now for the second part of the proof, instead of having what we had before of like the question mark y, since we did this first proof, it had to be an m. So there's no longer a question mark y, it's just m is equal to p. So here we can also do exact. Yep. And there's no more subgoals, and we're done. If we were to try to use auto in here, oh, it did actually work. I guess auto is a bit stronger than I thought. Sometimes auto isn't strong enough for these unification variables. There's an e-auto that can sometimes fill it in for you if auto doesn't work. But it seems like auto is working, so transitivity auto. Oh, I guess that was particularly strange. Ah, that was weird. So e-auto was able to fill it, but auto tried filling it with n. So what auto ended up doing is applying reflexivity here. And then the thing that we have left to prove in this side is n is equal to p. We didn't actually progress through m. So auto found this reflexivity first before it found the hypothesis, while e-auto managed to find the hypothesis before it applied reflexivity. So this is one of the cautions that we need to consider whenever we're using these unification variables. It might accidentally find the incorrect proof and unify it in a way that we didn't want. And we can sometimes get into a proof state that we can't continue verifying it anymore. Like it's not valid. So we want to be very careful with these unification variables. And it is much cleaner code to do this transitivity m, but it does take effort to write this m and specify like, oh, this is the m that I want to go through. So you'll see a mix of these things with e-transitivity and just if it's like just e-transitivity e-auto and it works, then it's fine. But if it was like transitivity auto, e-transitivity auto, and it doesn't work, then we're into some problems and we need to specify a little bit more information, like doing transitivity m instead of just e-transitivity. Well, I'll leave it as transitivity m because that is the slightly cleaner way of doing it. But so we proved these things for natural numbers, and that's not very interesting in itself. We want to prove these things about paths. And why is path a partial equivalence relation instead of a complete relation? Well, we do know that paths are symmetric and transitive. If we have a path from m to n, then we should have a path from n to m by just going through the reverse of all the paths, because we know that our edges are bidirectional, so it is symmetric. And we also know that paths are transitive by the way that we constructed paths. If we have a path, we can always add an extra edge. And so if we add a collection of edges inductively, then it would be the same as adding like a path to another path. So we do know that these that paths have the symmetry and transitivity, but what about reflexivity? Uh, for reflexivity for paths, it would mean that for any node, even if the node is not within the graph, the node there's a path from the node to itself. This seems sort of like a valid definition, but we want to specify that the paths are only valid for nodes within the graph itself. So basically, whenever we have a path, so like path path in graph for all p path g a b. So I guess we need to specify g a b. We know that nodes A and nodes B. Nodes GA and nodes GB. Yep. So whenever we have a path, we're also carrying around this extra information that the things that it is connecting are nodes within the graph. Uh, so we don't have reflexivity over any arbitrary node. We have a reflexivity only over nodes that belong to the graph. Or once we have a path, we are able to have reflexivity on either side. So let me do admitted for this. Admitted. Path refl left. So if we are given a path, then we know that there's a path from A to A. I guess we don't need to give this P a name here. I changed the for all into an implication because we didn't need to use the name P within the proof statement. Same here. So for alls and implications are basically the same, except that in the for all, you get to be able to depend on the name of the path within the rest of your lemma statement. But if it's just an arrow, then we say we don't need to depend on it. But you can do them interchangeably. So back to this definition here. Path GAB means that we can determine a path from A to A. Because we are able to know that from path GAB, we can extract out that A is within the graph. So we know that it is reflexive. So a partial equivalence relation, or a PER, has reflexivity over things that belong to the equality. So I guess we can start with proving this bottom one using the top proof. This one is easier. Intros GAB and P. And from this path GAB, we can use path in graph to be able to get out that it is within the nodes of G. So I will do this neat application because we don't need the path information after this. We can apply path in graph in P. And then we basically, with this applying within the hypothesis, it applies it into this thing, and we get out this thing, replacing the P for that thing. It is one of the styles that I like to do these kinds of proofs, although there is probably a cleaner way to do it. Uh, and then we can do destruct p as h, and then we don't care about the second half of it. So we are able to now prove that path GAA, I guess we had it down here, right? No. Uh, we can apply path refl. So path refl, from the construction of path itself, we're able to determine that it's a path there. And so now we just need to prove that GA, so that's auto. Cool. I don't know why there's this list node there. Maybe it came from this. That was a weird glitch. Okay, so if we have this path in graph, then we know that it's we are able to have reflexivity for paths. So we just need to I guess we could also do this for the right side, but let's just do this first. So infos G and P. How do we prove this for this path? Uh, so we can do this based on how paths were directly constructed. So we need to do induction. So induction P. And if we just do induction, it works, but it gives us arbitrary names for the things that it produces. So we're going to specify that we want to call it for the reflexive case. The reflexive case will have two inputs to it, the N and the H here. And see. Yep. So the N and the H got named properly. Like if we were to change this to N prime, it would change the name of it to N prime. But N is fine. And then for the inductive case, we have the inputs N, E, edges E, and a different path. So, and from this path thing, we will also have an inductive hypothesis. So we can do N, E, H, E, P, and IH. So N, E, H, E, P, and then the inductive hypothesis of P. That worked. So in the base case, where we have reflexivity, we have this assumption H, and both of the goals are basically just that assumption H. So we can do split auto. And now for this one, our induction hypothesis tells us that N is in the nodes, and we just need to convert the from into the to. And thankfully, we have the edges E is in the graph. So for our induction hypothesis, we don't need to even include this. So we can simply struct as hn, and then we can just ignore the second part. And if we do a split and auto, it will resolve this left-hand side, but it won't be able to resolve this right-hand side automatically, but to just simplify stuff. So split auto. So we have left to prove that G to E is within the nodes. Then if we take these edge definition, we know that the graph is edges closed. So the fact that this edge took us from something to something else means that both the from and the to needs to be within the nodes. So we can just directly apply edges closed. Might be angry at me. Nope, it worked. So when we applied edges closed, it just figured out that we need to have that edges E is in the graph, and which we already have. Yep. So we have proved reflexivity for path whenever that we have the knowledge that uh, there is a path that contains at least one of them. So like whenever there's a path from A to B, then we know there is a path from A to A and the path from B to B. Let's very quickly do the right hand side for completionist sake. And compared to this, we just need to switch around this thing here because we care about the B instead of the A. And then we should be done. Yep. That was very nice that it worked out. It's fun to like the most fun part about writing this kind of code is being able to chain combo things and then understand that like, oh, I just need to make this tiny change here, and it's the chain combo sort of just works out. You can write these really long tactics and apply them, and it's sort of like basically it's sometimes called type Tetris. It's because it just all fits together just right, and you can just get it to work out, and it becomes all green, and you're good. So it's a very much like a video game. You could call this a gaming stream. Okay, so we have reflexivity. I guess I'll just erase that reflexivity. Now we want symmetry. So I'll repurpose this into path. And so for all GAB, if we have a path from A to B, then we should have a path from B to A. So intros GAB and P. So we have a path from G to A. We want from A to B. We want to prove there is a path from B to A. So this is proven by reversing the path that we constructed P and going through the undirected edge backwards. So we also need to do a proof of induction here. I'll just copy the proof of induction that we had set up before. So for this part here, this one is fairly easy. The base case, we don't need to reverse anything. We just know automatically that from our induction hypothesis, like from the way that we construct it, we know that the n is within G. So apply path grapple and auto. And then for this one, we know that we have this path here. Uh, we have a path from n to from e, and our induction hypothesis tells us that we have a path from e to n. So we want to prove that there's a path from 2e to n. And how do we prove this? Uh, so the we want to be able to say that there. I think I had like a transitivity thing here. Yep, I'll move this up here because it was fairly helpful. Uh, so this is the unification thing that we had before. That we just need to add in the extra edge into the path. Ah, for all g. Uh, what is happening? Oh, I forgot to. I'll change this to a QE. Sorry for the changes. We're before in the bottom we had specified a particular graph G, so I could define everything in terms of that. But now we want to use this as a for any path G. Uh, so I guess we could even state it at the top. So we just need to quantify the for all G, and then because we are quantifying it there, we need to introduce it in there. So now we can use this lemma to construct this other lemma. Uh, we try and apply, it might not work. See what happens. Yep. It doesn't know how to find the from e, but if we remember our e apply, then it unifies it for us. And the this thing at the bottom, the 2 to n. Hmm. We just need to prove that there is a path from 2 to from e and an edge from. That's not what we want to prove. Hmm. I guess uh, this we can consider adding an edge to the left. This is adding an edge to the right side. We also want to be able to construct a path by adding an edge to the left side. So on this end. Uh, so I'll call this path edge right, path edge left. And we have from E, and then we can get to N. If we have a path from 2E to N, and edges from E and 2E are in the graph. And the one that we want to unify in here is the 2E, so I'll write that first. 2E from E. 2E from E and E. Let's see if we can verify this really quick. Uh, mm, I guess it's a lot harder to think live on stream compared to just doing this on my own. Uh, so I think this requires doing induction on P. And if we have a path from E to N, uh, so we want to revert the definition of from E. And H edge. So the reason for doing this reversion is that I want to have the least amount of things before I do induction, so I have a stronger induction hypothesis. Basically, I think that will help us. I'm not entirely sure, but when we do this induction here and we look at the second goal, then we're sort of locked in proving a very particular case from a known edge that we don't actually know that this edge exists, or induction hypothesis is not very useful. But if we revert it first, and then we do the induction, then our inductive hypothesis is defined over this arbitrary from E, so it's much stronger. Let's skip this part for now. We know that it has to be true. So we'll just submit it. We can always append one from the front. So the this should be true. And so path edge left. So we apply patch left F. We have left to finish off this thing here. Yep. And the auto. So we have left to prove that this flipped version where the 2E is the from and the from E is the 2 is within the edges. So that is definitely a bit weird, but we should be able to prove that using the fact that edges are undirected. Basically, from this E, we can flip it. So if we just apply undirected down here, it should immediately clear that up, flip it, upload the definition and get us just that we need to prove that E is within the edges, which is something that we have. So this path symmetric implies like we do need to know that we can append stuff to the left. But from that lemma, we are able to prove that it is symmetric. So let's go back to this proof here, figure out how we can append things to the left. Let's think about it a little bit more so that we don't get stuck in the proof. So we basically have like a to B, and then a B to C, and then a C to D. And, or rather, we have this C to D that is defined by adding stuff on the right side. And we want to add something on the left side. So I guess we just need to reconstruct it starting with a new start and then adding in all the things into it. So I'll erase this part here. And I'll do an intros from me and each edge that we had reverted before. So we are starting off with just knowing that there is an edge directly from E to N. I guess we could call this 2E to make it clear. So we have an edge from E to 2E. And we want to state that there's a path from E to 2E. So we can just fill that up directly via the path edge right. We apply path edge right. So we need to find an edge that is from E to 2E, which is this hypothesis that we already have. So E auto will finish this off. And now we just need a path from E to from E. And we get this from knowing that the edges with the from E implies that from E is within the path. So if we do apply path grepl, we know that we need to prove that nodes G from E. And we get that from the definition of edges by we apply edges closed. Does that work? Nope. So apply edges closed. And we want to do G of, or I guess we don't need to specify that there. Each edge. So does this work? Okay, it worked. So I'll explain this line. So the edge is closed. We see here that it has it's waiting on a graph and an edge. So those are the first two underlines. And then it's waiting on the proof that the edges GE is within E is within the edges of G. So these underscores here means that I'm not going to be telling you what they are. You should figure them out yourself. They become unification variables. And then this edge E is the exact proof that we have from a hypothesis that basically specifies what the G and the E should be. So by adding in this one lemma in here, the H edge, we are able to fully unify and figure out what the G and the E are. So Rocq is smart enough to fill in these gaps. I could have spelled out G and E in here, and that was not E. I would need to spell out the whole. I'll just copy this line. I would need to specify it out like that and it would still work. But that takes too much writing, so I'll just do 2 underscores. And it works. And that finishes that part of the proof. And now, once again, we have a path from E to from E, assuming that this is in the set of edges. We should be fine. Okay. Sorry for blanking out. So if we want to prove that there's a path from E to 2E, we this time we can't actually do this path edge because it does end in a 2E. So I'll directly do path edge instead of path edge left. And we need to know that E is within the edges, and there's a path G from E to from E. So I'll actually call this start instead of from E. That might make more sense. Yep. So and here we want to go from the start to the 2. And we know that from any start, we can get to the from. And we know that there's a from to n. And there's a path from what is 2e? 2e. I don't know, but we'll do this thing. Yep. Yeah. Maybe this one needed to be called 2e. Make it clear. So, yep. So we have now an edge from start to 2e, and we have an edge E. Let me just try to do the proof and see where we get off. So, we can fill that in. Oh, it just auto completed everything. That makes it difficult for explaining. Basically, we found this particular path here. I mean the edge here, E, so that was able to fill that in. I'll just do auto on this first part. And now we want to do a path from start to from E. So we can do the direct application of IH, which basically tells us that we can append one to the front. So apply IH. And then we just need to know that there is an edge from the start to the 2E. I guess this one should be it should be N. We need to know that there's a path from the start to N, which we have from H edge. So we should be automatically done. So if we just do auto, it's able to do all that for us. Now, let's see what happens. I think it will break if we remove this line here and remove these lines here. So we are no longer doing like the most general case. We are uh, just working with like the we are doing induction on this to-e without doing the induction on the from-e, like without generalizing over the from-e. If we go down to this thing over here, our IH is much smaller. And if we try to do this auto step here, oh, it still works. I guess we do not need to generalize. So this is actually a very simple lemma. It's hard to think about, but thankfully we don't need to think about that much because if it works, if this stuff is green, then we know that we got it right. That's very nice to know. We could even code golf this. Let's see what happens if we code golf it, because we are starting with path edge right on both of these. So if we do we apply path edge right e auto, yep, then we have left these two goals. Oh, I guess these are not the goals that we want to prove for the second case. This one came from down here. This will be completed from here, but here the e-auto filled this bottom one in with something that we didn't want to fill in. We want to fill it in specifically with the things that path edges fills in. So I won't code golf that. Yep. So now that we know that we have a way of appending edges to the right, we have a way of appending edges to the left, and we know that the paths are symmetric. Now we get down to transitivity. We want to be able to show the paths are transitive. So for all A, B, C within graph G, if we have a path from A to B and a path from B to C, then we should have a path from A to C. G, A, B, C, H, A, B, H, B, C. And so now, how do we prove this? We have two ways of proving it. We can either do induction on this AB and start adding it to the BC, or we can do induction on the BC and add it to the AB on the right. So it's like, it's certainly a lot easier based on the construction of how we did this, since path inherently appends to the right hand side. It is easier to do induction on the BC part and add it to the AB. So let's try doing induction without generalizing anything. So induction, I'll call this P1 and P2. So induction P2. So in the first one, we just want to know that there's a path from A to N, and we know that there's a path from A to N, which is P1. It's basically the reflexive case. We are immediately there. This one is just auto. Let's just do that here so that it gets resolved automatically. Now we have the second part. We want to know that there's a path from A to 2E. And we know that if we have a path from A to N, we have a path from A to from E, and we know that E is within the edges. So the first step here is to do the apply path edge, because we are adding an edge to the right, and we have it spelled out in this particular way. So this will be able to unify properly. We need to know that edges E is in the graph, and we need to know that path A is from E, which is exactly this goal that we have in here. And this goal can be resolved by this thing here, which is the P1. So if we do auto, it will complete both of these things. Auto. Cool. So with that, we have proven a restricted version of the reflexivity for paths. That it is reflexive for when it belongs within the graph G. And we have proven that we can add stuff to the right side as the modification of the thing that we did before. And we can add edges to the left side of the path as well. And then we have also proven that the path is symmetric. So we can flip around the A and the B, and it's entirely fine. And we have proven that we can travel through this middle B and get to a path from A to C. Now, if we remember at the beginning, we had the reflexivity, symmetry, and transitivity tactics. We won't be able to get the reflexivity one to work because we don't actually have reflexivity. We have like a restricted version of reflexivity. But we should be able to get the symmetry and transitivity tactics to work now that we've actually proven symmetry once. So let's copy this down here and show you what I mean. So also copy this line here. We would like to be able to just switch around the B and A by just doing symmetry. But when we try running this, it tells us the relation path G is not declared symmetric relation. You need to require the core lib classes relation classes library. So what does this mean? It means that we haven't done the work to say path G is actually a per. We need to specify it within the proof assistant to tell it like this is actually a partial equivalence relation. And so we should be able to look up and find the proper, we should be able to find this symmetry lemma that we proved manually and apply it in this particular case. So symmetry should be able to recognize that and apply it here. So how do we do that? We look at this relation classes library. We can copy this name here, relation classes. And we do a require import relation classes. So this line here imports the library and lets us use anything that's defined within that library. And as good practice, it's usually better, even though we can put it down here, it's usually better to put it at the very top of the file to specify what the requirements for this file are. So we require the import relation classes. And within relation classes, there is a thing defined called a partial equivalence relation, which is exactly what path is, because we have symmetry and transitivity. So in order to say that it is the partial equivalence relations, we need to define an instance of that class. So instance path per is for any graph G. We want to specify that path G is a valid per. So because of this instance here, this basically loads in the symmetry and transitivity, and we can, whenever we do this symmetry tactic, we will be able to refer to those things because it finds all these instances. So we have left to prove that the path is a per. And we can do that through the proof. So if we unfold per to see how it's defined, oops, yes, we can do a split. Yep. So if we split the per, we get that we need to prove that it is symmetric and that it is transitive. And these are exactly the things that we've already proven, that it is symmetric and transitive. So let's just try directly applying it. Does that work? Nope. What if we do intros AB? Yep. Intros ABH. And then apply path sim auto. And that worked. Maybe if I do an unfold symmetric, will that be able to? Yep, it was able to unfold it here. And then I think this tactic here will work. It just didn't unfold it automatically. Does that work? Yep, that was able to clear it off completely. And we can do the same for transitivity. Unfold transitive. Path trans. And with this, we have finished proving that path G is a partial equivalence relation. So, because it is an instance, it is now loaded in that whenever we want to do symmetry, we just look it up here. Whenever we want to do transitivity, we just look it up here. So if we go back down to this proof here, where we're trying to do symmetry again, if we do the symmetry command, it automatically flipped it, and we are just done by auto. So that is very cool. It's very cool how you can actually just load these instances and change how the tactics are. And if you do user-defined tactics, you can also do these crazy tricks like that and add in these instances. I wouldn't say this is like the best way to go about this, but it is like a very neat hack that we can just load all these instances, and it usually just gets resolved with symmetry. Sometimes you get the error where it's not able to find the proper instance, and so when we do symmetry, it will pop out a different goal that says, I couldn't find where the instance of this partial equivalence relation is. Can you give it to me again? So that sometimes happens, but for this case, it's just immediately defined right before in the same file, so symmetry will be able to find it properly, and it just works. This also works again for transitivity. So I can delete this thing here, and let's go to the transitivity. So once we've proven transitivity once, if we want to prove it again, if we do transitivity, it'll give us an error message, but it won't give us the same error message as before. It tells us that we need to know what it is going through, so same as we just say that it goes through the node B, and so now we just have left to prove these two things, so it's just auto. And additionally, we also have the E-transitivity tactic that works. So that cleared off the goals too. I guess we don't need this anymore. So I guess to recap what we've done so far, we defined the nodes as an arbitrary type and the edges as a way to connect the nodes. Then we defined the graph based on these nodes and edges with some properties about graphs. And then we were able to define path as just connecting the edges together through by appending one to the right. And we want to do this final proof here of path decidable. I guess I should move that down. So that's underneath all these things that we've already proven. And we describe path as a partial equivalence relation. So we know that if we have a particular path, we can determine that both of the sides of it had to be within the graph itself. And from that, we have reflexivity on the left-hand side and reflexivity on the right-hand side. But we don't have reflexivity for any arbitrary A and B. We just know that for any path that we already have, the A and B, we are able to determine reflexivity on both sides. Then we created these helpful definitions that just, I guess we should call these lemmas. Doesn't really matter, but we're able to append an edge to the right-hand side. This is unified in a slightly different way from how path is constructed. From path, we specify specifically we have an edge, and we do the from E and the to E there. But within here, we are unifying it differently. We unify in the hypothesis so that we can just directly apply this to any goal. It doesn't need to be in that format. And then we also have one for the left-hand side. If we have an edge on the left-hand side, we can add it to the left side of the path. And then from that, we were able to prove symmetry for paths and transitivity for paths. And then we loaded up the instance of the partial equivalence relation for paths within the Rocq proof assistant so that we can use the tactic symmetry and transitivity whenever we want to do proofs. Cool. Well, the second thing that I wanted to define in today's version, or at least like start discussing, the definition of graphs that we have here, it's a bit too, it's not restricted enough to be able to actually do proofs about graphs. And I'm not entirely sure how we're going to define it in the end, but I do have some ideas. Specifically, this graph could be an infinite graph because this node is just a function from node to proposition. So we can have an infinite amount of nodes. We have no restriction about what our nodes are. It's just an arbitrary type. We don't even know if there's a countable amount of nodes. It's just an infinite thing. And we have a property that just describes when it is in the graph or not in the graph. So this is a bit too wide of a thing because if we want to be able to do induction over graphs, say like remove one particular node and then prove it for the subgraph and be able to recover this proof for the subgraph back to the whole graph, it doesn't really work if we have an infinite graph. Because if we have an infinite graph and we remove one node, then we still have an infinite graph. So it's a bit weird there. We want to be able to be working over any arbitrary length finite graph and do induction over the size of the graph. So one way to do that is to change this into list node. Oops. So I guess everything breaks now, but with this list node, we now have like a structure that we can do induction over to determine like the full graph. We can break it down smaller and do induction over these graphs, and then use that to build a proof for the larger graph. And before we had everything defined in terms of the function prop of the node, so we need to redefine these nodes to adjust for that. So we know that it is within the nodes if the from E is within this list of nodes. So we changed it into this function called in nodes. In nodes. So here we're using the Rocq's predefined list library, where we have the in property just to grab the from E, like grab this element here and state that this element is found within this list. This should work, I believe. Oh, I guess we need to import require import list. Yep. So the error that it gave us was that in was not found. I believe that list.in would have been found. But we want to just use the word in. So we do need to do this import list at the top. Or it doesn't need to be at the top, but it is suggested to put it at the top, to say that we want to be using the list library and everything defined within the list library without having to do list dot. So, with this definition of graph, I think we need to change a whole bunch of places. So let's go and manually change all the places. In n nodes g, in a nodes g, in b nodes g. Hopefully these aren't too many places that we need to change. Oh, yep. I'm just doing it manually, even though we are probably going to have to change this multiple times. It's just fine because we haven't defined that many things yet. And I'll go ahead to comment out our example. We will probably be changing stuff a lot. And our example is just for demonstration purposes, so we can do that at the very end. So we have updated our graph definition to be like that. The problem with lists here is that we sort of want to say that graphs are equivalent modulo any rearrangement of this list of nodes. So we don't really want a list, we want a set of nodes, a finite set specifically. And we should be able to do induction over these finite sets. So before I actually delve into that, I'm going to leave that for the next video, because I do need to do some experimenting with sets within Rocq to figure out which set library and implementation we actually want to use. There's quite a lot, actually. And so for now, I'll leave it as lists, and know in the next video we'll be tackling that. The other thing that we want to worry about is that these edges, it's defined over an arbitrary prop. So the fact that it is prop means that we don't know whether for any given edge, whether that edge is within the graph or not. Because we might be able to find a proof, say like, oh, I know this edge is in the graph, so we're good. But if we don't have that proof that the edge is in the graph, we aren't able to uniquely determine that the edge is not within the graph. This is part of the constructive logic, where we don't have the law of excluded middle. Basically, we don't know that for any for all prop p, that either p or not p. We do not know this statement here for any arbitrary proposition, because this is a classical statement. It's within classical logic that we can do this law of excluded middle, and it's not computational. We don't have a way of just finding the opposite of an answer when we have the answer, because there's no way to construct the opposite of the answer directly from an answer. Unless sometimes it is possible. So sometimes there is a subset of things that are decidable. So like within our final proof, we want to be able to state that we can construct either the path or the not path directly. So in some instances, we do have the law of excluded middle, but we need to do a proof that there is the law of excluded middle, because otherwise this path decidable would just be done automatically, and we wouldn't have an algorithm to describe finding the path. We want to restrict ourselves to say that the law of excluded middle doesn't exist automatically, and then prove the cases where it does exist by providing an algorithm that's able to compute whether it exists or doesn't exist. So that's why we do want to restrict ourselves to constructive logic. We want to provide an algorithm. But that does mean that edges here, there is no algorithm to decide whether an edge is in the graph or not in the graph. So one way to do that, to fix that, is to do edges decidable for all e. Either we either know that edges e or not edges e. So we can add it as an additional assumption within the graph. This is one valid way of doing it. But if we want to make it look more like code, instead of having this prop and a case analysis on the prop, we can state that it is defined through booleans. So the boolean is going to be either true or false by construction. It is an object, and so if we take every edge and provide an object that says true or false, then we can say that we have a function from edges to bool. We either know that an edge is true or an edge is false. Then we need to say that the edges being true correspond to the edges being in the graph. And the edges being false correspond to the edges not being in the graph. So whenever we see these edges e, we need to change them to equal true to state that edge e is actually within the graph. So we're using the word true to represent that it is in the graph. We could have just as easily decided to use the word false to say that it is within the graph, but it seems more natural to say that when an edge is true, it is within the graph, and when an edge is false, it's not within the graph. So we do need to change all of these to equals true, equals true, equals true. Yep. So we have changed from a proposition into a bool. And so from the bool, we should be able to prove that uh, lemma edges side for all e for all ge, we can determine that either the edges ge is true, or that the edges ge is equal to false. So let's take a look at that. Or we can go one step ahead and say that it is not equal to. So we use the squiggly basically representing the prop version of negation. And I believe this should be provable. Intros GE. And the squiggly got changed into this representation. That's just a parsing thing. It parsed this in one way and then it unparsed it in a different way. But it's defined as the equivalent thing. So we look at this and we can uniquely determine the value of edges GE. We know that it is a Boolean, so let's see what it is. It's either true or false by the definition of how Booleans are constructed. So if we do a destruct edges GE, then it is either true, in which case we put true in everywhere, or it's false, in which case we put false everywhere. So in this first branch, just go left and auto. So left means that we need to prove that true is equal to true, which is just auto. And in this false is equal to true, we know that false is not equal to true, so we go into the right side branch. And we need to prove this thing. So to prove a negation, we need to assume a hypothesis and prove a contradiction. So intros H. And now we have H false is equal to true. And from this, we can do, based on the fact that it was constructed, we know that it's constructed in a different way, so they can't be equivalent. So we do discriminate H. And discriminate is just going to tell us like, oh, these two constructors have a different constructor at the head. Basically, false is actually a different constructor than true. So this cannot be equal, but since it's set as an equality, then we must have a falsehood and we should be done with our proof. So by stating that edges is a Boolean, we are able to encode that it must also be decidable. A proposition that it equaling true is a decidable proposition. So I guess now we need to change all of our places where we have edges E and do an equals true everywhere. So I'll just copy that part and see where it breaks. So in there, in there, in there, and that's it. So now, instead of just saying that we have a proposition, we have a Boolean, and we are comparing that Boolean to true. Cool. Now, the interesting part about this is that we do have two things that look very computational-like. It's basically what you would expect to see within the code. Like you have a list and you have edges. So if you're writing a program that works on a graph, you can basically extract out the list and the edges from this graph, operate on those, and then in the proof of it, of the algorithm working, you will impose that these list and edges correspond to a graph by having all of these hypotheses as well. And uh, you should be able to impose a proof of correctness on a piece of code that operates over lists and edges to bool by doing this kind of transformation. Uh, cool. I guess to recap on what we did there, to the changes of the graph, we want to set ourselves up for being able to do induction over graphs and finding like smaller graphs of graph. So we changed nodes into a list of nodes that we can do induction over, which will then be changed into sets so that they are unordered. And then we defined edges as a decidable proposition so that we can computationally decide whether it is in the graph or not within the graph by just saying that we have a boolean, and whenever it's true, it represents it being within the graph. So it is decidable. And the rest of the graph remains the same. We just updated to membership within the list for all the nodes and change the edges to being equal to true as the indicator. That's it for today. In the next video, we'll look into defining the node as a set instead of a list, and we should be good. Thanks for watching, and I'll see you guys next week.